Hi Falcons, what I'm going to talk to you about today is covalent bonding. In covalent bonding, electrons are going to be shared between two or more atoms. So it's a contrast from ionic bonds where an electron was transferred from one atom to another. In this case, both of the atoms in question need to gain electrons to become more stable, meaning they both have a strong level of attraction for a valence electron from a nearby atom. This attraction causes each one to pull on the other atom's valence electrons until their valence shells are overlapping. And then those two electrons are shared between the two atoms. When this occurs, this would be referred to as a molecule. A molecule is defined as something that's made up of two or more covalently bonded atoms. Molecular compounds and covalent bonds typically form between two non-metal atoms, two atoms that want to gain electrons to become more stable. Let's take a look at it using Lewis dot structures. In this example, we're going to talk about the element chlorine. Remember, chlorine is in group 7A, so chlorine would have 7 valence electrons, needing to gain one in order to become more stable and have that full octet. If chlorine was to come in contact with another chlorine atom that also needs to gain one, they would both have a pull on the other atom's valence electrons. What would end up happening is they would then pull themselves closer together, and then these two electrons would become shared between them, meaning that each atom of chlorine would then have 8 valence electrons. The one to the left could consider these its 8. The one on the right would consider these its 8, and these two would be shared between them. The formula for this compound would be Cl2. An easy way to remember this concept with covalent bonding is that many students find it useful to think of covalent as a form of cooperation, and when you cooperate, you share, and they are sharing these valence electrons. Now let's talk about some of the properties of molecular compounds. They have a relatively weak intermolecular attraction compared to what's occurring in ionic bonding. Now that's not to say that the covalent bond itself is weak. This covalent bond formed by shared electrons between oxygen and hydrogen is in fact very, very strong. But each one of these molecules is an independent unit, and the attraction between the molecules is weak compared to the chemical bonds that are holding all of an ionic compound's crystal lattice together. Again, here in this example of a diatomic oxygen molecule, this double bond, covalent bond, would be very strong, but the attraction of this oxygen molecule to another molecule compared to the chemical bonding in an ionic compound's crystal lattice would be relatively weak. As a result, molecular compounds tend to be relatively soft solids, think waxes, plastic, sugar, things like that, liquids or gases at room temperature based on that strength of attraction in between the molecules. So again, not the strength of the covalent bond, but the attraction between the two molecules. Molecular compounds, as they don't contain any charged particles, do not conduct electricity well under any conditions. They're very good insulators, so they would not conduct electricity in solid, liquid, gas state or when dissolved. Another interesting property of molecular compounds is that they can form very small molecules like this diatomic, made of 2 oxygen atoms, to incredibly large molecules. Some of you might be thinking, this sugar molecule looks quite large, but in comparison to a double helix in a DNA molecule that contain millions of atoms in one molecule, you can see that there's a wide range of compounds that can be created through covalent bonding. One interesting class of compounds created through covalent bonding are what are referred to as covalent network solids. These are formed by a repeating pattern of covalent bonds or shared electrons. Examples would be diamond or quartz or graphite. They're composed of nonmetals, but they actually create a crystal structure like an ionic compound. The difference being that instead of being held together by that alternating positive and negative ion structure, they're held together by a repeating pattern of covalent bonds. Diamond, for example, many of you would be aware is made out of carbon. Carbon, which is in group 4A, can make 4 covalent bonds. It needs to gain 4 electrons to become stable. So in a diamond, that causes this carbon atom to bond to 4 other carbon atoms. And if you look through this diagram here, you'd see that each carbon atom is bonded to 4 other carbon atoms with these incredibly strong covalent bonds, which is what makes diamond one of the hardest substances on Earth. Another type of carbon compound is graphite. However, in graphite, the carbon is not being bonded to 4 other atoms, rather it's being bonded to 3. And this allows the graphite, which is also made of pure carbon, to form sheets. And those sheets can be scraped off on a piece of paper in what we would typically consider or refer to as pencil lead. Properties of covalent network solids is they are very, very hard, like the diamond, and very strong. They have very high melting points due to this interconnected network of strong covalent bonds. Like other covalently bonded compounds, they are also poor heat and electrical conductors. Here are some examples of covalent network solids like we talked about: diamond, silicon dioxide or quartz, and then the graphite in your pencil lead. This one again is bonded into flat sheets, which can be scraped off when you're writing on a piece of paper. Hope this was helpful. Thanks, Falcons. Have a good day.